Okay, now today we start to explore another important component of a smartphone in particular, and of an electronic system in general. Can you hear me in the back, or should I use a microphone? Can you hear me? Really? Okay, so we let's say start to look at how power here is distributed in electronic systems, and of course using our reference system, that is the smartphone. So the power delivery network, as it is called, has to let's say receive power from the battery, which is typically now a lithium-ion battery that has a supply voltage of about 3.7 volts when it's in full charge. And then from that battery, several electronic subsystems have to be supplied, and they require different levels of voltage and different currents. For example, the CPU has a supply voltage which is typically about 1 volt. I say about 1 volt because the typical situation is that in order to preserve as much as possible battery life, the supply voltage required by the CPU is changed. You probably remember the fact that we have discussed together that the power consumption of a digital circuit is something like 1/2 the total C, the total capacitance of the circuit, times the supply voltage squared times the frequency. Let me just write this power, the dynamic power, which is the single most important component, is 1/2 the total capacitance of the chip times the supply voltage squared times the clock frequency times the activity factor, which is on average the percentage of gates that switch at any given clock period. Okay, in the current use of CPU, what happens is that when the load is low, so you do not need that many computation cycles per second, one wants to decrease the clock frequency. And which is good because one can decrease the power consumption. And actually, if you decrease the clock frequency, you are also able to reduce the power supply voltage. You remember that the power supply voltage determines the delay time of the logic gates, and therefore the clock frequency. When you want to reduce the clock frequency, you can increase the delay time of the logic gates, and therefore you can increase the delay time, and therefore you can decrease the supply voltage. And this is the reason why you have typically this range. Okay, this would be full throttle, so maximum speed, and the other one would be a situation in which you want to reduce power consumption. So more or less what happens is that the dynamic power, including the dependence of the clock frequency on VDD, is proportional to the VDD to the third power. Okay, there's a more or less a linear dependence of the clock frequency of VDD. So and therefore a reduction of 50% of a reduction of 1/3, let's say, of the supply voltage actually means a reduction of more than half of the power consumption. So this is something that is typically done. Then we have a different voltage for the DRAM, a different voltage for the audio codec, because you have to with this part you have to supply typically also the voltage to the loudspeaker. Then there's the voltage for the analog part of the camera, which is still different. Then there's the display backlight, that they are LEDs and then require an even higher voltage. And then in addition to that, let me just add also that you have the flash memories that you need to provide supply voltage to, and they require something like 20 volts, or more often plus 10 volts and minus 10 volts. Typically these 20 volts are given in plus and minus 10 volts. You also need that supply voltages. Oh, sorry, I'm using the upper part of the screen. Okay, in the next. So the reason why flash memories are not present here is that typically flash memories are only have a supply voltage of about 1 volt, and then internally in the chip they have the DC-DC converters in order to obtain the higher voltages required for the programming and the erase operations. Okay, so they are not provided by the power delivery network. They have an input voltage of like 1 volt, and then internally obtain the higher and lower values of voltage. Okay, but as you can see, this is pretty complex. You need a DC-DC buck converter in order to go from 3.7 to about 1, and then you also need it to be controlled by the operating system, because it's the operating system that knows at the low level when you can go slower with the CPU, and then can adjust the conversion factor of the DC-DC buck converter. Then you have also these other converters that are called LDO. This LDO probably is an acronym that you have never encountered before. LDO stands for low dropout regulators. LDO is slow dropout, and basically they are linear DC-DC converter. Linear, not linear, linear DC-DC converter. These are linear, right? You have seen an example of a linear DC-DC converter with feedback during the first course in electronics, and the principle of operation is essentially the same. The most important characteristic of LDOs is that they can also work with a very low difference between the input voltage and the output voltage. But apart from that particular aspect, in their essence they are linear voltage regulators. The DC-DC buck converter and the buck boost converters are switching regulators. Okay. Also, and I've seen you have seen examples of switching regulators, but in this course I want to enter in a little bit more in the detail of the operation of buck converters and boost converters. Okay. Then you need again the audio one thing that to stress here is why for some applications you really need a DC-DC buck converter, and for other applications you need an LDO. And let me just let's say recall the main differences between the two. A buck converter or a boost converter are switching regulators. These are switching regulators. and they typically have high efficiency. And this is a plus, a great advantage of switching regulators. They also have a drawback in the sense that you have ripple in the output, and you can also have some disturbs. The ripple and the disturbs are related to the fact that they have a switching operation. So you have an internal clock that switches on and off transistors in order to perform the conversion, and this is a disturb that propagates also to the block that they power supply. And this is the reason why typically if you want to supply a block which has to be, let's say, sensitive to a small signal, for example an analog amplifier with very high with a very high gain, or a camera for which you want to have a very high gain because sometimes you have a poor signal, or audio which has the same problems, you typically prefer to have a supply voltage that has no such ripples and no such disturb. And for this reason these blocks are supplied by an LDO. So these are linear regulators for which you have low efficiency, you pay in terms of efficiency, and this is a minus, but then you have no disturb, and this is the plus. For example, also for DRAM you need no disturb, because there's a very let's say sensitive operation that DRAMs have to perform, which is the sensing of the bit line. Do you remember we talked about that? In that case you have a comparator that has to verify the difference between very close voltages, and in that case you want no disturb. For this reason you use an LDO in order to power supply them. Okay, so these are the main differences, and of course you need many of them because you have different output voltages. Okay, this offers also another possibility, which is the one of the possibility of switching off completely a block. If you do not want to use the camera, you switch off completely everything, the camera and the LDO, and you have no static power consumption in the whole block. You want to switch off the display, you can switch off the display and switch off also the converter, so everything is down, and so on. So for this reason it is very useful in order to optimize energy consumption in the system. Okay, this is done at this level, at the level of the single system. You need to understand that in the case of multi-core systems this is also done in the chip, at the level of single blocks of the chip that can be completely switched off. So this situation with the many converters and many LDOs at this level is in the board, in the main board of the smartphone, but the trend now is to replicate the same system within the chip with different DCDC converters and different LDOs that provide the supply voltage to different blocks in parallel. So it is something which is occurring in a fractal way. Where is this power delivery network situated? It is situated in the chips that are called PMIC. These are power management IC. If you remember the example that we have discussed at the beginning of the iPhone 6, there are two power management integrated circuits in the board, and each of them, for that reason, contains all the several DC-DC buck converters, boost converters, and LDOs. Okay, when I say several, I mean in the order of few tens, let's say 20. Okay, this is the order of magnitude. Okay, so what we need now is to look a bit into the details of the operation of a DC-DC buck converter and of of a boost and of a buck boost converter. So DC-DC converters are used, of course, in portable electronics, not only in smartphone, in all portable electronics, but they are also used for the driving of DC motors. That for the moment is not of interest for us. So the typical situation is the one shown here in the figure. You have a line voltage or a battery. If you have a line voltage, you typically need a diode rectifier in order to have an unregulated DC current here. Then you typically have a filter. Let us follow the direction after the battery if we focus on a smartphone. Then you have a filter. This is an unregulated DC current, and then here you have the DC-DC converter. Therefore you have the DC regulated voltage, and therefore the load, which is the block, the circuit that you want to provide energy to. The only difference when you have let's say an AC line in order to get energy from is that you need a diode rectifier before the whole chain. Now there are different types of DC-DC converters. We focus on the first three of them, which are interesting for us. The step down, which is also called buck converter. Step down means that the output regulated voltage is smaller than the input unregulated voltage. So if you have a battery with 3.7 volts, you use a buck if you want to have a DC regulated voltage smaller than 3.7 volts. Then you have a so-called step up converter, also called a boost converter, that is required if you want to increase the voltage by using the same by obtaining the same sign. And with a buck boost converter, the third option, you are able to change the sign of the supply voltage. For example, if you need a -9 volt for the programming operation of a flash memory, you need the buck boost in order to obtain -9 from 3.7 volts. You need to invert the voltage. Okay, just pretty fast. We want to discuss the initial concept and then the quantitative aspect. The simple concept is the one of using PWM switching. PWM stands for pulse width modulation, and it is very simple to explain. You have an input voltage which is not regulated, and then you have an output voltage that is regulated. This R symbolizes the load, and in general it's the system to which you want to provide a power supply. The simple thing that you can do is to move this switch in such a way as when you turn the switch on, you provide in the output VD. When you put the switch off, you provide 0. And if you switch it on and off frequently, you provide a voltage which is in an output on average between 0 and VDD, depending on the duty cycle of the turning on and off operation. And therefore, by changing the duty cycle, you can change the average voltage that you can provide on the output. Okay, this is the main concept of all types of switching regulators. The output voltage is something like this: VD when the switch is on, and 0 when the switch is off. So if T on is the duration of the portion of the period during which the switch is on, and Ts is the period of the switching cycle, then of course the output voltage is equal to the input voltage times the ratio of T on to Ts. Right? Now, of course, very often on the load you do not want to have a rectangular wave. You prefer to have only the average, but in order to do that you can of course filter. You can use let's say a low pass filter in order to obtain only the DC value of this rectangular wave. So okay, how can you build such a filter? Typically you can use L and C components, inductors and capacitors, because they are lossless, at least in principle. They do not dissipate active power. But of course this is true only in an ideal world in which you do not have dissipations, and in which you do not also have let's say dissipations due to the switches and the inductors and capacitors. Let's see in practice how this works. This is the situation that in practice you have. This is the switch that I discussed before. This is the step down. We are talking about reducing the output voltage with respect to the unregulated input voltage. Then you have the switch as before. This LC block is a low pass filter. You can see that it is a low pass because for the DC current in DC the inductor is a short circuit, the capacitor is an open circuit, so this node has the same voltage of this one in DC. For high frequency, on the other hand, the inductor is an open circuit and the capacitor is a short circuit, so the output becomes 0. Okay, if you want to compute analytically let's say the expression of the transfer function of this low pass filter, it's pretty easy it's a calculation that is pretty easy to make. You have a two-pole filter with a cutoff frequency, so a second order filter with a cutoff frequency which is given by this expression, is 1 over 2 pi times 1 over the square root of LC. It's pretty easy. It is something that is obtaining by just writing the transfer function, which is a voltage partition between C and L. So here you have a rectangular wave as before, and here you only have the DC component. The important part is that you have to be sure that the cutoff frequency of the filter is much smaller than the switching frequency. This is the switching frequency. So that you're actually able to cut off the switching frequency and all the harmonics, and you only keep the DC value. The other important difference with respect to the ideal situation that we have discussed earlier is this diode. you have just to consider what's the role of this diode. This diode has the role of putting this node to almost 0 when the switch is off, because you can see when the switch is on, you have current flowing in this way through the inductor, right? When you move the switch off, the inductor is inertial with respect to the current, so continues to draw current and draws current from the diode because the switch is off. So in order to draw current from the diode, puts the voltage on this node to minus V gamma, so almost 0, and puts the diode in conduction in order to continue to draw the current. So actually you have the situation in which when the switch is on, this voltage is VD and the diode is off. When the switch is off, this voltage is practically 0, actually minus V gamma, and the diode is on. So again, this is the situation. This is diode off, and this is diode on. And in this way, the diode avoids the voltage spikes, because if there was no diode, then when you switch, when the switch would be turned on, this voltage would go very high, very low in order to continue to draw current from the switch. So you would have a voltage spike on the switch. If you have a diode, there's no voltage spike because the diode can provide the current. So you see, the situation is now pretty simple. The main, let's say, knob you have in order to adjust the output voltage is the duty cycle of the voltage controlling the switch. If you increase T on with respect to Ts, you increase V0. If you decrease T on, you decrease T0. And then the regulation would occur exactly by controlling the output voltage and, as a consequence, adjusting the duty cycle of the switch. Now, if you look into the circuit with some more detail, we can understand some different types of operation, because there are actually two different modes of operation. One is so-called continuous conduction, which means that you always have current through the inductor. Now, if we want to consider this type of operation, we can focus on the voltage applied to the inductor, so-called VL. Okay, of course, when the switch is on, which is this situation, the voltage applied to the inductor is VD minus V0, this level, right? For all T on, when you have a positive voltage applied to the inductor, I mean, and this is a definition of inductor. Actually, the current through the inductor increases linearly with time, because just by definition of inductor, you have this expression, the derivative of the current with respect to time is proportional to the applied voltage divided by the inductance. So when VD minus V0 is constant and positive, we have a derivative of the current with respect to time which is constant and positive. So the current through the inductor, which is IL, increases linearly with time, right? Then during, and this is the circuit, you have VD here and then the rest. Then during the next part of the time period, of course the switch is off. Let's look at this other situation. The switch is off, so you have 0 here, because basically we are approximating the diode, the voltage on the diode when the diode is conducting with 0. You have a 0 here, and here you have V0. So the voltage applied to the inductor is minus V0, this one. And of course the current decreases in time with a constant slope, which is minus V0 over L. And this is the situation. And then the cycle starts again. So the in the so-called steady state, in stationary conditions, you have a periodic behavior. So this situation is exactly equal to this one. So the current at the end of the cycle through the inductor must be equal to the current at the beginning of the cycle, and this means that the increase in current during T on must be equal to the decrease in current during T off. And if we equate the two things, we can of course obtain the a relation between the output voltage and the input voltage. Okay, let's follow this part. Of course, if we write, this is the increase during T on, VD minus V0 over L times T on. This is delta I. And this is the decrease during T off, V0 over L times T off. Okay, they have to be equal, so the difference of the two has to be 0. And then of course you can remove L and L. You can you see here you have minus V0 T on minus V0 T off, but you know that T on plus T off is equal to the switching period, and therefore you have something like VD times T on is equal to V0 times Ts, and therefore V0, this is not a 0 actually, this is VO, it's for output. V output is equal to VD times T on over Ts, which is the relationship that we had discussed at the beginning. Now, the important and the defining aspect of continuous conduction mode is that the current through the inductor, even if it varies significantly during the period, is always positive, therefore larger than 1. And this must be this is a requirement, because the current in this T off time goes through the diode, and the diode can only conduct a positive current. Okay, but of course things can change. If the average current absorbed by the load is reduced, then this starts to move down, and then you could obtain that this point goes below 0. And this is a situation that we must check. Okay, let me go through it into some more detail. Okay, this is the thing that I've already shown. And then, so this is the limit of continuous conduction. As I said before, this is the current through the inductor. You can see that as you reduce the average current through the load, you can reach this situation in which the minimum current through the inductor is exactly 0. Okay, this would be the limit of continuous conduction, because if we reduce further, then the current would go below 0, which is not allowed by the presence of the diode. Okay, so let's discuss a bit this limit. In this limit we have that the amplitude of the ripple, which is the peak current minus 0 divided by 2, is equal to the average current absorbed by the load. This is the limit, right? This is I peak, so I peak over 2 is equal to the output absorbed by the load. This is something that we know, and this is something which can be reduced if the load absorbs less power, and then at some point the two situations, the two terms can be actually equal. This is very important in practice, because in modern let's say electronic systems, you have strong variations of the power absorption. For example, you have a device which goes in standby mode, and then when it goes in standby mode, it strongly reduces power consumption, so that you can actually go easily from continuous conduction to a state of discontinuous conduction. Okay, let us look into the detail. What is this I peak? This I peak is what we before called delta I. So it's T on, if we compute it during the T on part of the period, T on times Vd minus V0 over L. And then we have to divide it by 2. We bring this 2 from the previous expression. This is the delta I that we had computed before. Then we can call T on as D over Ts. By definition, D is by definition the duty cycle T on over Ts. And then you also see that we can exploit the fact that V0 is VDD times T on over Ts, so is VDD times the duty cycle. So we exploit this second expression in order to put VDD out of the parentheses, so that we have D times Ts in the place of T on. Then we have Vd times 1 minus D in the place of Vd minus Vo. And then if we put all the things together, we can what we can do is the following thing. We can collect Ts times VDD over 2L and actually add a 4 here and multiply by 4 the numerator. And then we call this part I lbmax. Why this is useful? Because if we plot the current for which we have the limit of continuous conduction, so the limiting current, as a function of D, this expression has the maximum in 1, so in 1, which means ILBmax, when D is equal to 1/2. So it's a parabola with respect to D, and the maximum of the parabola is exactly this expression. So you have to keep in mind that D depends on the value of the output voltage that you want. So once you know the unregulated voltage and you know the output voltage that you want, you also know D, and therefore you know the current for which you go at the limit of continuous conduction. Okay, so above this parabola we have continuous conduction, below this parabola we have discontinuous conduction. And in a typical DC buck converter, is very common to go continuously from continuous conduction to discontinuous conduction, as a function of the current that the circuit is absorbing, which means the power that the circuits need. So let's look at what happens in discontinuous conduction. This is the same plot as before, but with a slight difference. You see, here we plot the output current. This is the output current, as a function of V0 over Vd. In continuous conduct for a constant Vd. So Vd is the unregulated voltage is constant, and here on the y-axis we have the ratio of V output to Vd. So this is the parabola that we have drawn before. It's the same thing, because in the case of continuous conduction, and therefore also in the limit of continuous conduction, we have that D is equal to V0 V out over Vd, Vo over Vd. So this is exactly the same parabola as before. If we use here as a factor, as a parameter for this family of curves, the duty cycle D, basically given independent of the current that you want on the load, for a given D you have a constant output voltage. This is the significance of these horizontal lines. This means that when you are in continuous conduction, for any current, the only factor that determines the output voltage is the duty cycle, because this relationship is valid. Okay? This is continuous conduction. This is the parabola as before. This is the limit for continuous conduction, so above this parabola on the right side of the x-axis, and below you are in discontinuous conduction. And we need to understand exactly what happens in discontinuous conduction. So let's look at that case now. So in discontinuous conduction, you are in this situation. The current has a time period during which it increases, which is the T on as before, from 0 to a peak. So it starts from 0. Then you have another time period during which it decreases linearly down to 0, and then it cannot actually go below 0 because the diode does not allow current to go in the other direction. And then you have a third final period during which the current is exactly 0. So you have 3 phases, and then of course the cycle restarts. So just to consider all possible cases, you have we can, let's say, divide the switching period Ts into 3 segments. One is DTS as before. During this time the switch is on. Of course. During the other time the switch is off, but we subdivide the other time into smaller time periods. One is delta 1 TS, during which the switch is off but the current flows through the diode, and therefore another time interval delta 2 TS, during which the switch is off and the diode is off. So you have no current whatsoever. Of course, the sum of D times delta 1 times delta 2 must be 1. Now you can see that the situation is slightly different with respect to the previous case, but still we can write the an expression which gives us the peak current and allows us also to compute the relationship between the output voltage and the input voltage. What's this relation? Of course, you can write here the increase in current during the time during the switch is on, so during T on, and this is the slope of the current, which is the voltage applied to the diode over L times the length of time, which is dTs. So this is the slope, this is the time, and the product of the two is the increase in current. And then of course it must be equal to the decrease in current during the time delta 1 TS. So during delta 1 TS the slope is, except for the sign, the voltage applied to the inductor, which is V out, VO, over the inductance L. So you put the two things together. Of course L goes away with L, TS goes away with TS, and then you are left with an expression which now includes also delta 1. Okay, from the points of view of the expressions, the things are pretty simple, but it's only important to understand what is actually happening in the circuit. So let's continue with this consideration. You can then extract VO. Of course you have two terms with VO times D and VO times delta 1. Once you do that, you bring all the terms with VO on the right side, and then you can express VO over VD as a function of the rest, which is D, which is multiplying VD, over D plus delta 1. It's also easy to check that the two things work, because if in the case of a continuous conduction or in the limit of continuous conduction, delta 2 becomes 0, and therefore D plus delta 1 becomes 1, and we are, let's say, in the previous case. Just as a check that the expressions are correct and the things are working. Okay. Now, in the following of this consideration, we will assume that VD is constant, and that therefore, if VD is constant, we want to obtain VO as a function of the other parameters, considering VD as a constant. This is the situation that one typically has in this example with motor drives, or in other example with a constant battery voltage. The battery has a given voltage, and therefore VD is constant, except for very long times, because of course the battery can go down. But for a shorter time interval, one can consider VD constant when the power supply is a battery. Then, if one wants to change the output voltage, one has to change the duty cycle of the switch. And this is actually how it is done. Now we are here. What do we do now? Actually, what do we do is the following thing. We'll keep this expression and for I peak, for the peak current, and substitute in the place of VO this expression, the expression given by here. So you see, we move this in the place of VO, we write VD times D over D plus delta 1, and we copy the rest. So we just took VO from this expression, we put it here, and we obtain this one. Okay, now that we have that, we need to we can simplify things, and again, you will see later why we do that. We typically call this part, which is all constant, because those are not parts that we can move now. We call this ratio divided by 8 I lbmax, and then we multiply by 8. You shall see what actually this lbmax is, and it's pretty easy to know. This is exactly the previous expression. Actually, we had already defined that, and this is the maximum current that you can have when you change the duty cycle, and in particular when you have a duty cycle equal to 1/2. If the duty cycle is equal to 1/2, you are in the limit of current conduction, or constant conduction. Also delta 1 is equal to 1/2. So the sum of D plus delta 1 is equal to to 1/2. Then this is 1/4 times 8 becomes 2, and therefore the peak current is twice the constant current that you have at maximum at the limit of continuous conduction. Okay. Now, from here, we want to compute the average output current, and in order to do that, we do the same this calculation. The average current is the integral of the current over the period, the switching period, divided by the switching period. So we need to have that the area of this triangle below the current must be equal to the area of the rectangle which has a base equal to the switching period and the height equal to the average current. So we compute the area of the triangle area of this triangle, this one, sorry, this triangle. You see, this is the peak, is I peak. D plus delta 1 times Ts is the base of the triangle divided by 2. And this must be equal to the area of the rectangle, which is IO times Ts. So that we can obtain now IO. Of course, Ts and Ts go away. And if in the place of I peak we substitute this expression, look here, this is what we wrote before. Then we take this expression, we move it here, this part goes away with this part, Ts have already gone away, here we have 8, here we have 2, they go away and become 4, and therefore if you copy everything, we have I output is equal to 4 I lbmax times D times delta 1. Okay, I'm just discussing all the passages, then we arrive at the final expression, which is useful at the end. Once we write that, let me just show you why we obtain this expression, which is the final one for us. Essentially, let me just show you. When we have this, we can write IO over 4 I lbmax is equal to D times delta 1. This product, D times delta 1, it's too low, right? Yeah, and the best thing would be to let's say replay the video also on the screens that you have on the table. Or there's no possibility for that, but I don't know what to yeah. On the blackboard. No, this part. Okay. Okay, I can do that. I can do that, but it can also crash. You know, I prefer not to touch anything now because no, so let me write here. So you can see this part. Okay, I can write here. I can write IO over 4 I lbmax is equal to D times delta 1. Okay, now the I lbmax is a constant. You know already how it's defined. IO is the current absorbed by the load. These two parameters somewhat depend on the voltage, because if you look at the expression that I wrote before, it's easy to extract something that is related to the product delta 1 times D. It's enough to multiply the numerator and the denominator by D, so that we have D squared on the numerator, and on the denominator we have D squared over delta 1 times D. So we simply can take delta 1 times D from this expression and put it here. So delta 1 disappears from the expression. We only have that the ratio between the ratio of the output voltage to the input voltage is equal to an expression which only depends on the duty cycle and on the current, which is the one written below here, which I can understand. It's easy, it's difficult to read, but essentially I only substituted delta 1 times D with IO over 4 lbmax. Okay, and this is exactly the expression which is required in order to, let's say, complete the part related to discontinuous conduction in the previous graph. So let me just go now to the other graph, and we can put this expression here. I'm rewriting everything, so you should follow anything completely. This is just to summarize everything. So before we considered only the part, let's say, in which the current was higher than 4D times 1 minus D times I lbmax, during which we had continuous conduction. In the case of this continuous conduction, when the, let's say, complementary expression is satisfied, the ratio of VO over VD is given by this expression that we have computed, and if we plot it for constant D, we obtain something like this. It's easy to write this expression because you see that when D goes to when I/O, the current, goes to 0, then this expression has to go to 1. So all the curves have to go to 1 in this point. And then, of course, must also be connected to the case of continuous conduction on the limit. Then, of course, we can plot the expression in other ways, and they all do this type of behavior. So this is the complete curve, which gives us the output voltage as a function of the input voltage for any current. So just let me repeat once again. Let us assume that we want to have an output voltage which is half the unregulated voltage. If the current is high, we have to keep the duty cycle to 0.5. If the current becomes lower than this value, then we need to progressively reduce the duty cycle in order to keep the current constant. Because of course you cross here these curves at constant duty cycle, going from 0.5 to lower and lower duty cycles. Of course, this type of behavior have to be taken into account by the part of the circuit, of the logic circuit, which actually performs the regulation of the switch converter. So if you consider for a minute the complete DCDC switch converter, let's think about what you need. You need one switch, you need one diode, you need one capacitor, you need one inductor, and you need typically a finite state machine or a microcontroller in order to perform the regulation. Okay, this finite state machine essentially has to know whether the output voltage is increasing or decreasing with respect to the value that you want, and dependent on it has to adjust the duty cycle. So in the most complex DC-DC regulators, this is done by a microcontroller. In the simplest situation, this is done by a simpler finite state machine, but you need to have some. All these components are typically integrated except for the inductor. Inductors are as of now difficult to integrate, especially the large inductors that you need for these DC-DC regulators, and therefore they are off chip. So you need to accommodate on the board one chip for the DC-DC regulator plus one inductor for because you cannot integrate it. Okay. In typical power management ICs, you have several DC-DC regulators, and sometimes you have several output, let's say off-chip inductors around the chip, because every DC-DC converters needs one inductor. But there are additional architectures in which you can use the same inductors for more than one DC-DC regulators. So you have a smaller number of inductors than the DC regulators that you have inside the chip. These are, let's say, more complex architectures that we are not going to see together, but just to give you a complete picture of the whole thing. Okay. Okay. Now I want to stress a bit the comment that I did before regarding the ripple. Of course, you have an output ripple. You know, you have this switching wave that is filtered by the LC filter, but of course it's not filtered completely. Therefore, the output voltage has a superimposed ripple. So let's look at the at the size of this ripple. Of course, this is something that is typically unwanted. For some circuit is not a huge problem. For analog circuitry and sensitive circuitry, as I said before, it can be a problem, so you want to eliminate it. But let's look at the ripple. So again, this is the voltage which is applied to the inductor, is Vd minus Vo during the T on, and is minus Vo during T off. And this is the current through the inductor, IL, which goes up when VL is positive and goes down when VL is negative. We already did this plot. Now we want to focus on before we focused on the maximum value, on the minimum value, and on the average. Now we want to focus on this part. Let's say with respect to the average current, which is this one, this is IO, which is absorbed by the load. You have for half a period you, let's say, give more charge to the load, and for the other half period you give less charge. This is relevant because the additional charge, let me repeat this, let me put it here. This is the circuit, right? This is the load which is absorbing IO. This is the current through the inductor. Let's assume that the load absorbs a constant current. So the additional charge delta Q is absorbed by the capacitor during this half period, and of course during the other half period the current in the inductor is less than the current absorbed by the load, and therefore the capacitor gives the charge back. Okay, this is exactly what's happening. So the capacitor is there to absorb excess charge and to release excess charge when this charge is needed. But the point is that when the capacitor absorbs the charge, the voltage on the capacitor increases, and you see it as a ripple on the voltage supplied to the load. So let's compute this charge. This delta Q is obtained by computing the area of this triangle. So 1/2 times the height of the triangle, which is delta IL divided by 2, and times the base of the triangle, which is half the switching period, Ts over 2. So the current ripple, okay, we did already compute it before. This delta IL is, you remember, this is computed during the off state, is VO over L, which is the VO over L, which is the slope in the off state, and 1 minus D times Ts is T off. So this is delta L, which I can take and put here in order to, let's say, compute delta Q, and then I can compute delta Q, and when I have delta Q I can compute the ripple delta V0, which is delta Q over C. This delta V, this is not 0, this is O. Delta VO is the variation in the output voltage, which is of course called voltage ripple. So it's delta Q over the capacitance, and so by substituting everything we can essentially 2 times 2 times 2 becomes this 8, C becomes this C, and delta L gives us VO over L times Ts, which becomes squared because it's multiplied also by this Tms, times 1 minus D. There are two things that need to be noticed here, is that the ripple is very much dependent on the switching period. So the faster the switching of the switches, the smaller TS and the smaller the ripple, as one can imagine. And it also depends on this LC. You remember that 1 over square root of LC is the cutoff frequency of the filter. So if you want to reduce the ripple, you need to have a high inductance and a high capacitor. Okay, they typically have a cost. No? The cost of an inductor and a capacitor is proportional to the inductance and the capacitance. But for these reasons, you need to have high inductance, and therefore you need to have it off chip. You cannot have a high inductance on chip. In some cases, also the capacitor is off chip. Most modern circuit typically is done inside the chip. Yeah. Just to add a remark, this is also one of the reasons why in modern DC-DC converter one typically reduces TS as much as possible. Of course, it's important to have the ripple at a frequency which is not actually, let's say, problematic for the load that you want to supply, because of course you need to be sure that this frequency of the ripple does not interfere with the operation of the circuit that you want to supply. So this is an additional consideration that one has to make. Okay, now let's look at the other architecture. We can go faster because the main concepts I think have been already clarified now. Another situation is the one in which you need an output voltage that is larger than the input one. This is pretty as you remember before, by construction the output voltage was equal to the input voltage times the duty cycle, which is always smaller or equal to 1. Okay, if you want something that is larger than 1, you need to change the circuit, and this actually can work. This actually can work because we are actually changing the position. If you look, we actually have modified only the position of the diode and of the switch. With this architecture, we are able to obtain an output voltage which is with the same sign but higher than the input one. Again, let's look at what happens in the two cases. When the switch is on, here, actually current goes in this way. So you apply VD to the inductor, so the current through the inductor is positive and increasing linearly in time. Okay. Since well, I can't say it now, but even if it wasn't the case, nothing would change. Actually, since this output voltage is high, the voltage applied to the diode is negative, and therefore the diode is off. And also the output, this is the load. The load is, let's say, isolated. Okay. What happens is in the inductor is that since the energy in the inductor is proportional to the current squared, when the current increases, the inductor is accumulating energy. Okay, the inductor is accumulating energy in the magnetic field it is generating, and therefore it is going to release it in a later time. So the inductor, you have to think it acts exactly as a capacitor, but with the current instead of with the voltages. When you charge a capacitor, it means that you apply a larger voltage and then you store more charge in the capacitor, and the energy, let's say, stored in the capacitor is therefore proportional to the voltage squared. In inductor, you stored charge in the magnetic field, and that charge is proportional to the current squared. So you charge an inductor, you energize an inductor by increasing the current, and then you have some energy that you can spend later on. When the switch is off, as in this case, of course you do not have this loop anymore available, but you have current in the inductor. The inductor is inertial with respect to the current, and the current flowing through the inductor pushes through the diode and goes to the load. Actually, what happens here is that the inductor increases the voltage on this node until the diode goes on. When the diode is on, of course, current can flow. For this reason, the diode, this voltage is increased by the inductor. Basically, it only drops by V gamma on the diode, and here you can have a voltage which is higher than Vd. So it is the inductor that pushes on the voltage in order to push current through the diode, and this is the mechanism according to which you have an increased voltage. You are exploiting the spike of the inductor. Of course, in order to do that, the inductor is releasing energy. Is releasing the energy that it has accumulated before. Okay. Now, this is a qualitative explanation. Let us look at the, let's say, wave, at the behavior of the waves. Now, first, again, continuous conduction, and then discontinuous conduction. So, again, this is the voltage applied to the inductor. During this period, the switch is on, and therefore you have Vd on the inductor, and during the following period the switch is off, therefore you have Vd minus Vo applied to the inductor. Also here we are discarding the component of the voltage drop on the diode. So during this period you have a current increase because voltage is positive, and the slope is Vd over L. This is the circuit. As I said before, this is the situation. The Vd is directly applied to the inductor because the switch is on, and the diode, of course, is off. During the following part of the period, then here you have a diode which is on, and so we are, let's say, treating it as a short circuit, and then current goes through this direction. The voltage applied to the inductor is Vd minus Vo, and of course is negative, and the current is decreasing, and the slope is Vd minus Vo over L. Vd minus Vo is a negative quantity. Okay, so again, as we said before, one can assume that in the steady state you have periodic conditions, so you can compute the quantity by which the current increases during T on, the quantity by which the current decreases during T off, and the two have to be equal, and therefore this is the expression that you make. So Vd over L, this is the slope times T on, and then the other slope, Vd minus Vo over L times T off. They must be equal. T on plus T off is the switching period, and by playing with that expression you can obtain the output voltage as a function of the input voltage and the duty cycle. This is easy to do. You just have to simplify L with L, then just to simplify the expression, D is the duty cycle, so T on is D times Ts, and T off is 1 minus D times Ts. Then if you substitute both, you obtain Ts and Ts that you can simplify, Okay, here yeah, so maybe it's useful to make another passage intermediate. Here you have, instead of T on, you have D TS VD plus y minus D TS VD minus VO. If I just substitute T on and T off from here, and then you see that here you have VD times D times TS and 1 minus, so you can simplify this and this, because they both are multiplied by TSVD and TSVD. For the first expression, no, it's not the proper way of writing it. No, it's better not to write it this way, but actually this part and this part go away, so you only have TS times D, which is this, so TS times VD, which is this part, and then 1 minus D times TS times VO, which is the second part. Okay, and just discard this simplification because it's only on one part of the equation, not on the other one. When you have this, of course, you can simplify TS and TS, and therefore you have VO as a function of VD. Essentially, VO is equal to what about the sign here? No, sorry, this is there's a sign which is wrong. This is a minus, because this was a minus, this goes here. Okay, this has a minus here, so when you have VO is equal to VD over 1 minus D. Okay, so again, the output voltage is equal to the unregulated input voltage divided by a quantity which only depends on the duty cycle. And of course, you can see that by construction, the output voltage is larger than the input voltage. And this is of course required because the current has to decrease for some time, and if the current decreases, it means that the output voltage is higher than the input voltage. So this is something that is, let's say, ensured by construction. You have an output voltage that can be in practice also very high. If D is close to 1, you can have a very high output voltage. Practice not extremely high, but a few times the input voltage is possible. Okay. Now this is again expression. Now this is let's say a consideration which can be interesting. You see that during one part of the cycle and during the other part of the cycle, the DC-DC converter does not have losses, because you only have a capacitance and an inductance that are lossless. So in this ideal case, which is only ideal in practice, in which do not have losses, of course the power provided by the input must be equal to the power provided by the output. And this means that the product VD times ID, the power at the input, must be equal to the power at the output. So this is interesting to keep in mind, because since we know the ratio of the two voltages, we can also know the ratio of the two currents. That would be reverse. Of course, this is based on the assumption that there are no losses, which is actually not always true. Now, it's not, I mean, rigorously is never true, but sometimes the losses are significant. Okay, as you can see, also in this case, there's the issue of discontinuous conduction, because if the current absorbed by the load decreases, then this dip here can touch zero, and then you are therefore at the limit of continuous conduction, and one in that case has to do similar considerations with the as the one that we did before. So what are these considerations? This is the average current, which is also equal to the ripple at the limit of continuous conduction. So Vd times T on divided by L is the increase in the current during the part of the period during which the current rises, divided by 2 is the average current that we, so at the limit of discontinuous conduction, this part which is Vd times T on over L divided by 2 is the average current, and this is what we write here. Then we know how to write it, because Vd is Vo times 1 minus d, and T on is Ts times d, and then we have 2L at the denominator.